Well, hello there. Got another example for you. This time we're going to make you into rocket scientists, just like Homer Hickam, or for some of you, more like Quentin. Okay, so we're going to take off and do this problem. See, you still have to suffer my humor, even though I'm not in class with you. Okay, so let's work this problem. Okay, what is the net force acting on a 1,000-kilogram rocket, which blasts off and reaches a speed of 1,000 meters per second in 10 seconds? What is the applied force from the rocket propellant? This is a frictionless problem. Okay, just went ahead and put that in there because you could have air resistance, right? Like air friction, air resistance. Okay, but we're not going to consider that. So let's take a look at this problem, and to begin to understand the problem, we're going to do what? We're going to draw a little drawing. Okay, so we draw a rocket. Okay, USA. Okay. We're going to put the forces on the rocket. There's an applied force pushing it up, isn't there? And there is, if we can get it in there, good, a weight force that's resisting that. So we want to go over and start doing our sign conventions and our symbology. Up and to the right is always positive. So the weight's acting straight down. That's the negative. We need to remember that. We need to start talking about what our symbols are going to be. So I'm going to use this force. Okay. M is mass. A is acceleration. APP is applied. What else do we need? Oh, weight. Weight. What is weight? Weight is mass times gravity, so we got to have gravity. And that's, as you will recall, 9.8 meters per second squared. Okay, so we have pretty much what we want to look at. Oh, since we have some units here, we want to go ahead and say newtons, NT for newtons, so we don't confuse that with a normal force. We don't have normal forces. The instant the rocket takes off, those normal forces are gone. Okay, so what we have acting on this rocket then, nothing horizontally at all. We don't need to consider the horizontal forces or calculate any of those. We just say, hey, these two have to be, not equal, because this one has to be higher than that one or it won't take off. Okay, so we have a net force, okay, equal to mass times acceleration. Okay, but we weren't asked for acceleration. We were asked for what is the applied force. Okay, so we have to figure out what this net force is, and all we know is the acceleration. Okay, well, do we know the acceleration? Actually, we do. Okay, it blasts off and reaches a speed of 1,000 meters per second in 10 seconds. Well, what is that? Okay, what does that tell us? An acceleration, doesn't it? Okay, so acceleration is nothing more than a change in velocity over time. We have that change in velocity, right? It's up is positive, and so we go the final speed, okay, minus the initial speed over time, and that's just 1,000 meters per second divided by 10 seconds. And so our acceleration then, we have figured it out, 100 meters per second squared. Meters per second squared. Okay. So we know the net force then is equal to mass times that. So 1,000 kilograms times 100 meters per second squared times conversion factor of 1 Newton is a kilogram meter per second squared. And we're going to have a net force of 100,000 newtons. See, the kilogram, second squared, meters, leaving your newtons, 100,000 newtons. What does that tell us? Well, we also know that that net force, okay, is made up of the forces on the object, and that's the weight and the applied force. We'll put a negative sign on that weight, right? Or we could put the applied force minus the weight. Okay, so 100,000 newtons is equal to applied force minus the weight. What is the weight? Okay, the weight, we'll just do a little box over here and say mass times gravity. Okay, right? What's the mass? 1,000 kilogram. Gravity 9.81. Okay, so the weight is what? (1,000) times 9.8 is 9,800. Okay. Kept looking at that. Okay, so rearrange and solve. The applied force, okay, is equal to 100,000 newtons. Minus, to be clear, 9,000. Oh, sorry. When I rearranged, should be a plus 9,800 newtons. We rearrange that equation. Okay, let's make that clear. Goes into when you rearrange. Okay. And the applied force then is equal to nothing more than 109,800 newtons. And we box our answer. We're done. We're rocket scientists.